Hello everyone. Today is the day 10 of 75 hard research challenge. I'm going to talk about what I did yesterday, that was on day 9th. So yesterday I gave a lecture on what is RLHF and what are its problems for aligning a large language model for human preference dataset. So today I'm going to continue that lecture and discuss what is direct preference optimization and how it like removes the problems from RLHF. I'm going to go through a detailed derivation of the same. So let's get started. Okay, so yesterday we saw what is RLHF and it has three steps. One is fine tuning using supervised fine tuning, second is learning a reward model R phi XY, and third was learning the final large language model which has been adapted to the human preference dataset using R phi. Right. So today we are going to talk about direct preference optimization. So this was the paper introduced in NeurIPS like 2023, and since then it has been cited well and people have shifted from RLHF to DPO. So the problem with RLHF was that for training an RLHF, to train pi theta, you have to keep three large language models in the GPU memory. Second problem was that fundamentally reinforcement learning is a very unstable process. To train a reinforcement learning is very unstable and has a lot of hyperparameters, so it's not a very straightforward task. So the question that the authors of DPO asked is very simple, that can we incorporate the reward function this and into can we reformulate this reward function into a optimization problem directly, which so that we do not need to train an explicit reward model and then use the explicit reward model to train the final or to fine tune the final large language model. Okay, so they say that the policy network in this case being the final large language model that you want to align for human preferences. So they say the policy network represents both the language model and the implicit reward function. This reward function is going to be the same that RLHF has used. That means it will be same as the Bradley Terry preference model that they have used and devised a reward formulation based on that. They are going to do some mathematics so that you don't have to train the reward model explicitly and then use it to align the large language model to preferential data. So the main section of the paper is section 4, and in this section I'm going to focus only about the derivation, and we see that they directly jump to from one equation to another equation, but they give a very detailed analysis of this in the appendix of this paper, which is section 8.1. So I'm going to go through this rather than jumping directly to the one equation to another, giving hand wavy arguments, because that's what I found in most of the videos online, right? So I spent some time on it and I think I have figured it out how they go about it. Okay, so let's first start with what they do in RLHF. To revisit that, they have an optimization problem where they want to optimize a reward loss function that has two parts. First part is this, they want to maximize this particular reward that was learned in the second phase of RLHF. So this particular objective function is that of RLHF. So they want to maximize the reward, but they also do not want to deviate too much from the reference LLM that they start with. Okay, so pi represents the current large language model that you are training. Pi ref represents the model that you started with, and because both of these are probability distributions, so you do not want to move away from too much from pi ref, so you add a penalty term that while you maximize the reward, you should also not move away too much from your reference large language model, and this is achieved by subtracting the KL divergence. This beta is a parameter that is used to control how much you are allowing this penalty term to weigh in the final loss function, and then you simply do a maximization over the expected value over the examples, that is the prompt coming from the dataset, and the y, that means the generated content coming from the policy pi, which is the current large language model that you are training. Okay, so what do we do here? How do we go about it? So this is pretty straightforward, right? This is the same equation they have copied. Second, what they do is that uh, they simply write the function for KL divergence. They simply expand it. So usually KL divergence between P and Q, that means DKL P and Q, is given by that expected value, or rather let me just expand it. It simply says that Px sum over x Px and log uh, log of Px by Qx, right? Okay, so what does this mean? But in this case, if you notice that there is only log of pi y given x divided by pi ref y given x, right? There is no sum over x Px, right? I should have used better nomenclature here. So ideally, if we would like to have this term expanded as sum over y pi y given x, right, log uh, log of pi y given x divided by pi ref y given x, right? So this is what we want, but notice that this particular term is missing from this equation, and the reason for that is that the probability, because you are sampling the next word, let's say this is the prompt that you have, right? And you want to generate the next word, then this word is generated in this token, rather is generated using first you predict the probability distribution over this word, and then you sample it. So because you have sampled it, all the probability mass lies on this, right? So this is essentially 1, right, because you have sampled it. So that's my intuition for this. I think I'm please correct me if I'm wrong. So this turns out to be that this becomes equal to 1, and because you have sampled only one of the y, so sum over y also like reduces to a single element, right? So you're left with only this particular term, right? And that is what they have done here. Okay, so this is how it is done. Okay, now next step is that you simply you have a maximization here, so you simply turn it into a minimization problem by taking the negative out of this particular expectation. So you simply reverse these two terms here. This is the equation that you have now. Now this is the interesting part where I do not find any explanation that how did they come from this particular equation to this particular equation, and I think I have some idea of it, how they did it. I mean, algebraically it makes sense how to do it, but why did they think about it? Why did they say that okay, I want to jump from this particular equation to this particular equation? Is that if you notice, I want to get rid of probably that's what they thought, or maybe that's how I will think that I want to get rid of r somehow, right? That was my original motivation. So let me expand this particular equation. Okay, so it was log of pi y given x divided by pi ref y given x. So let me take this equation and do log exponential 1 by beta r x comma y, right? Apologies, r x comma y. So what does that mean? I simply took a log and exponential here, right? That's all I did. So next what we do is that log of m minus m, log of m minus log of m is simply log of m by m, n, right? So we are reduced with log pi y given x by pi ref y given x into exponential of 1 by beta r x comma y, right? This is what we are left with, right? Okay, so now that we have this, why didn't we stop here, right? Why did we go, how did we think about going from this equation to this equation where we have a zx, right? And what is a zx? Zx is a normalization thing, right? So my intuition says that okay, I want to convert it into a KL divergence, let's say, and I say that this, for example, this looks very familiar to what we saw here. This was a KL divergence term, right? So how do we go from this to this? For turning this log likelihood log term, log ratio, log of this ratio into a KL divergence, we want both of them to be probability distributions, right? So how do we, but upper one is all, numerator is already a like a distribution, right? But the lower one is not a probability distribution, because now you have multiplied it by a scalar vector which is greater than equal to 0, right? Essentially. Okay, so how do we convert any distribution, any unfactored distribution into a probability distribution? Is that we simply divide it by a normalizing term, right? And that is where this term is, that zx is coming into picture. So how do we do it? That we say that let me divide this numerator by zx, where zx is given by this particular term. What do they do? They say that okay, I have zx here. I have zx is equal to pi ref y given x into exponential of 1 by beta r x comma y sum over all y. Okay, so if I sum over all y's and then divide this sum of to like to this particular term, then it becomes a probability distribution, right? So that's what they have done here. Okay. But if you divide something out of nowhere, you have to multiply it with something also. So they divide and multiply and divide it with z of x, right? So that's what they do. They say that log of pi y given x divided by z of x by z of x, pi ref y given x exp 1 by beta r x y, right? Okay. And what they do is that they take this particular term and use the same formula, right? We had this formula, right, with us, that log m by n is equal to log m minus log n. So they take out this particular zx term, and this equation turns out to be this equation, right? That's all they did, right? Because if you have log of m minus log of n, then it will turn out to be log of m divided by zx, and this zx will cancel out with 1 by zx, right? So we'll return to original equation that we have like defined here. Okay, so this is how they move from this particular step to this particular step. Okay, they say that once you have this, we note that this particular function z of x is a function of x alone, because you have summed over all possible y's, right? Okay. And they say that let us just simply define pi star equal to this particular denominator. Okay. So now both pi y given x and pi star y given x are probability distributions, because pi star y given x is divided by a normalization constant. Okay. Why is it a valid probability distribution? Because all the values of pi star are greater than equal to 0, and they all sum to 1, as we have normalized, right? Okay, so that's all they do, and they simply put this value here, and now we note that this particular value does not depend on y, right? So we can push the expectation of y only to this particular term, whereas keeping the expectation over x to all these two terms. And that's what they did here, that they pushed the y expectation inside only for this particular term, and x is an expectation over both the terms, right? So now you can see that they have simply said that this is nothing but a KL divergence term between pi y given x and pi star y given x, and this. Okay, so now this is a constant independent of pi. Okay, when, because we want to minimize it over pi, when does this term or both of these terms become minimum? Okay, because this is independent of pi, so we cannot change it, so it is a constant with respect to pi, of course. But this term, whenever this term becomes minimum, the whole term will also become minimum. Okay, so when does a KL divergence become minimum? They say that it becomes minimized when at 0, if and only if both the distributions are identical. Okay, so we have an optimal solution here, that pi is equal to pi star y given x, sorry, pi y given x is equal to pi star y given x is equal to the formula that we derived in the previous page here. Okay, and that's all. That's what they are saying, that we have an equation of pi in terms of the reward function, right? So now we can use this equation of pi y given x represented in the form of zx as a function of zx and reward function, as well as the pi reference policy. We can use this to optimize or find the value of pi y given x. But there is a catch in this, that is, this particular function zx, also known as partition function, has a equation which has sum over all y. So that implies that, for example, we saw it here, right? So this sum over y is what makes it intractable, practically intractable, because y, what is y? Y is the next token to be predicted given a particular x, right? So this y will belong to the vocabulary. Sorry, the y will belong to vocabulary, and as you keep on generating the sequence, this blows up exponentially, right? So it's not feasible. So how do we fix that? And that's where they derive certain more equations. Let me go through it once more. Okay, so what we can do is that we can find the value of r x y here in terms of pi y given x and zx. Okay, so we just algebraically rearrange these values. Let's see how to do it. Okay, so we take the zx to this side and pi ref as denominator in this side. So what we get is that we have zx, okay, into uh, pi star y given x divided by pi ref y given x, right, is equal to exp 1 by beta or x comma y, right? So now this again, to if you want to take, we take log on both sides. We take a log here and we take log here. So this will turn out to be that rxy is equal to, after taking log, we can take the beta to the other side. So simply rewriting this, we get beta log of zx into pi star y given x divided by pi ref y given x, right, y given x. Okay, so now we can again break this log function into two parts, where we use the formula that log mn is equal to log m plus log n. These are very basic formulas, probably you already know, but it's always good to reiterate. I'm just crossing all the t's and dotting all the i's here. So simply this equation reduces to this particular, this equation reduces to, let me just write it down, that we get r star is equal to this particular value, right? Beta log pi star y given x plus beta log z of x, right? So now let's see. So once we have this with us, right? So let's see what happens in the when we apply this, because earlier in RLHF we all used Bradley-Terry preference model for human preferences, right? So we would want to we would put this value of r of x that we found here into this particular formula of Bradley-Terry, right? So what was Bradley-Terry? We can look at my previous video, but in short it says that if you want y1 preference to be the probability of y1 greater than y2, that means y1 being preferred over y2 given x, then it is modeled as exponential of r star x y1 divided by the normalization term, right? So when we put the value of r star here, which we derived here, like, okay, what we get is this particular equation. Okay, we're simply putting the values. Okay, so now what happens is that this can, what we here, how do we reach from this equation to this equation? You simply do that divide by this particular equation, right? So this turns out to be 1 by 1 plus 1 plus uh, 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 this particular equation. How do we go about this? Is that it will be, so there is a step here that you have 1 over 1 plus exp beta log pi star y2 given x by pi ref y2 given x plus beta log z of x, right? So and then what we do is that we have another term here that says that exponential of beta log pi star y1 given x by pi ref y1 given x plus beta log z of x, right? So now what we are doing is that we see that when we have these two terms will turn out to be subtracting each other in the exponential power. That means exponential a minus v will be there, where a is the numerator and b is the denominator. So what we get is that these two terms cancel out with each other, right? And you are left with this minus this. Okay. So that's what they have done, is that they have this particular value that you have y2 given x here, y2 given x minus y1 given x. So now this equation looks very familiar to 1 by 1 plus exponential of some term, right? This is nothing but our good old sigmoid function, where sigmoid function is given by sigmoid of z is equal to 1 by 1 plus exp minus z, right? So that's what they have done. Okay, so they have an exponential term here. Let me just delete log zx. Yeah. Okay, so yeah, this way. Okay, so that's all they have done. That when you up, so what they have done in appendix A.2 is that when you have derived a value of r of x using equation number 15 and you put that r double x into equation number 16, you get that this particular term turns out to be sigmoid of this particular term, right? And now it is very straightforward, right? So what you have done is that that we did in RLHF also, that you use this particular, let me just move these formulas somewhere else. Yeah, I'm going to move it here. Okay, so what you have done is that you have derived the Bradley-Terry preference model in terms of the pi star optimal function that you optimal policy and the pi reference policy that you have. Okay, so now we are going to use this to define a loss function, that like we did in our that case, in the case of RLHF. Okay, so that's what they have done in the main paper, that once you have this preference model, you can simply say that loss DPO is nothing but negative likelihood of log likelihood of the Bradley-Terry preference model, right? And that's it. So now you can say, if you compare it with the RLHF one, I think they have provided it. Yeah. So in the case of RLHF one that we had here, the difference between these two is that let me see if I can. No, I cannot. Okay. So the difference between these two is that here you have a reward function with you in the optimization function. Here, however, in the case of DPO, what they have done is that they have gotten rid of the reward function, and the whole policy or the optimization function remains in the term of the policy that you want or you are optimizing, and the reference policy that you do not want to move away from. Okay, so that's what they have done. In terms of the loss function, let's see what the loss function does. Okay, or the gradient of the loss function does. Okay, so that's what they have done. They have they have derived an equation for the gradient of DPO, which will be equal to gradient with respect to theta of this particular equation, right? Okay, so this will turn out to be, let me just go ahead and write it down. I'll try to be as concise as possible. Apologies for moving down. Okay, how do we go about it? They say that gradient of theta, right, expectation of gradient is gradient of expectation. A gradient of expectation is equal to expectation of gradient. You can say that. So we let me just simply write of some term u. Okay. Now if we do that, the gradient of log term is 1 by sigmoid u into gradient theta, where u depends on theta. Let's say gradient of theta sigmoid of u theta, which will again be 1 by sigmoid of u theta into sigmoid u theta into 1 minus sigmoid u theta. You can try to derive this on your own, but the gradient of sigmoid is sigmoid into 1 minus sigmoid. Okay, into gradient theta u theta. Okay, because of the chain rule. Now these two terms cancel out, and this is what we are left with. Right. So that's what they have done here, that you are left with, and then you also have this. That's what they have done here, right? You're also when left with a beta here, because when where u is equal to this particular term. Okay. It's pretty straightforward from here on, that you are left with this particular value when you expand this, which is essentially saying that beta times the sigmoid of 1 minus sigma, also the 1 minus sigmoid is equal to sigmoid of minus u. Okay, so that's what they have done, and simply the gradient of this term is left. Now when we go back here, we are left with this particular equation after some algebraic manipulation here, where r is given by beta log pi theta by pi ref. Okay, so now let's first understand what is going on here. It can be the gradient term can be divided into two parts. It says that increase the likelihood of y winning, right, and decrease the likelihood of yl, because there is a minus here and there is a positive sign here. But at the same time, whatever like the gradient or the difference of these two gradient comes, you weight using reward estimation. Okay, so you say that if the difference between the loss and the winning is very high, then and the sigmoid of that is very high, that means you weigh it accordingly, right? So that's what they say here, that intuitively the gradient of loss function increases the likelihood of the preferred completions yw, that's what they have written, and decreases the likelihood of dispreferred completions yl, that means this. Importantly, the examples are weighted by how much higher the implicit reward rates the dispreferred completion scaled by beta. That is how incorrectly the implicit reward orders the completion, right? And accounting for the strength of KL constraint, that is beta. Okay, so this is the derivation of DPO. Essentially what they did is that they simply reduced they simply took the optimization function or the loss function for RLHF and tried to get rid of R theta, specifically in the case when you are using preference model of Bradley-Terry preference model. So that's all for this particular video. Thanks for watching.